section 2.5 is about something called the second derivative. I have hinted at the idea of a second derivative before. In the context of free fall, you take a ball, throw it straight up, let it go up a bit before it comes back down and hits the ground again because of gravity. If h is your height as a function of time, height, say in meters, as a function of time, t in seconds, its derivative, its rate of change is called the velocity. And with free fall, where you throw the ball straight upward to begin with, the height function will be a quadratic graph as a parabola opening downward, looking like this. Careful, this is not the path of the ball. The ball is not traveling like that because I didn't throw it like that. I threw it straight up. This is not h as a function of distance, it's h as a function of time. This graph is just saying the ball goes up a ways before coming back down and hitting the ground at h equals 0 when t is right there. The derivative of this, dh dt, f prime of t is its rate of change, and that is the velocity. Velocity is the rate of change of position in general. In this case, height is the position, and its units would be units of h per unit of t, meters per second. This would be in meters per second. T is still time. That doesn't change. The input doesn't change what it is. It's the output that changes units and interpretation. The graph of the velocity as a function of time, of the derivative, is a graph that gives you the slope of this graph. Starts out positive, then becomes 0 right about there. Then the slope becomes negative. And if this is a quadratic we've seen before, that its derivative will be linear, the graph of velocity as a function of time will be a straight line looking like that. Starting out positive because I throw it. The moment I let it go, that's time 0. For a certain amount of time, it keeps going up with positive velocity, but it's slowing down until the moment in time where it reaches the peak. That's that instant the velocity is 0. Then it starts moving down where the velocity becomes negative because it's moving downward. The absolute value of the velocity is the speed, but we're talking about velocity here, not speed. But that's a function too, a nice function. It's got a derivative as well. It's called the acceleration. Acceleration is the derivative of the velocity with respect to time. Its units would be units of v, meters per second, per unit of t, seconds. Meters per second, written meters per second squared. That's just shorthand. Meters per second squared is shorthand, convenient notation that really means meters per second. It's the derivative of velocity, but the velocity itself is a derivative. So it's a derivative of a derivative, a second derivative. If you wrote this dv dt Leibniz notation in this way, which is done sometimes, d dt of v, realize v is a function of t. This is called operator notation. And if you then replaced v with dh dt, it's almost as if you could multiply these and write d squared h dt squared. Yeah, are we really multiplying? No, we are not. Oh. Remember, I said calculus is full of convenient fictions. One convenient fiction that we're seeing here is pretending these things are fractions, dh dt, dv dt. Another convenient fiction is to pretend ddt and ddt are getting multiplied here to get d squared dt squared, and the h just gets stuck there. It's not multiplying. ddt and dht, I can't multiply those things. They're just symbols telling me to take the derivative. You can't multiply such things. But you might say it's kind of fun to pretend you can. And so we pretend, and we go ahead and use this notation for the second derivative. With the function notation, however, we just do another prime, and well, why bother with all those parentheses? Just write f double prime of t. All these different symbols here, 1, 2, 3, 4, 5, 6, 7 symbols, all mean the exact same thing. A represents the fact that we call it the acceleration. This represents the fact that it's the rate of change of the velocity with respect to time. So does that, except now I'm thinking of ddt as an operator. Take the derivative with respect to t of this function of t. And here I'm using the fact that v is the rate of change of the height with respect to time. And here I'm pretending to multiply. This is just a notation thing. Notation, equality, definition. There I'm emphasizing that the derivative, the second derivative, is the derivative of the derivative. I'm also emphasizing that here. And here's just shorthand notation for that. And these are all notations, really. A lot of these, at least. Just different notation for the same idea. The acceleration is the derivative of the velocity. It gives you the slopes of the velocity, but the velocity is a straight graph here. Constant slope, constant negative slope. The acceleration is a constant function. And in standard units, it would be negative 9.8 meters per second squared near the surface of the Earth. By the way, the acceleration due to gravity is smaller, or closer to zero, I should say, on top of Mount Everest. Did you know that? It's probably more like 9.7 meters per second squared. And if you're on the moon, it's also different. It's more like 1.6 meters per second squared. Something like that. If you're on Mars, I don't know, 3 meters per second squared. It depends on the planet or the moon. It also depends on how high you are. It's not really constant. It's just approximately constant. So when we're close to the surface of the Earth, so we take it to be constant because that's convenient for modeling purposes and getting reasonable answers.